Welcome back everyone to this part of the sequential circuits. In this part, we will discuss about the synchronous counter. So in asynchronous counter that we have already discussed earlier, what we have seen, asynchronous counters are serial counters, right? They are slow because each flip-flop can change state only if all the preceding flip-flops have changed their state. That's what we have observed in asynchronous counter, right? The propagation delay in case of asynchronous counter gets accumulated and so causes problems. If the clock frequency is very high, the asynchronous counter may skip some of the states and therefore malfunction. So this problem is overcome in synchronous or parallel counters. Synchronous counters are counters in which all the flip-flops are triggered simultaneously. That means in parallel by the clock input pulses. Whether a flip-flop toggles or not, it depends on the flip-flop's inputs. It can be either J, K, D, T or SR flip-flop. Since all the flip-flops change their state simultaneously in synchronization with the clock pulse, the propagation delays of the flip-flops do not act together to produce the overall delay in this case of synchronous counter. In fact, in this case, the propagation delay is equal to the propagation delay of just one flip-flop plus the propagation delay of the gates involved. Okay, so the synchronous counters, they can operate at much higher frequencies than those of that in asynchronous counters. Okay, now we will see how to design a synchronous counter. Okay, what are the steps to design a synchronous counter? First step is to decide the number of flip-flops. Based on the description of the problem, we need to determine the required number n of the flip-flops. The smallest value of n is such that the number of states capital N should be less than equals to 2 to the power n and the desired counting sequence. What is step number 2? We need to draw the state diagram. First, we need to draw the state diagram showing all the possible states. A state diagram which can also be called the transition diagram. It is a graphical means of depicting the sequence of states through which the counter progresses. In case the counter goes to a particular state from the invalid states on the next clock pulse, the same can also be included in the state diagram. What is step number 3? Choice of flip-flops and excitation table. Once the state diagram is drawn, then we need to select the type of flip-flops to be used and write the excitation table. An excitation table, it is a table that lists the present state, next state and the required excitations. Then once the excitation table has been written, we need to obtain the minimal expressions for the excitations of the flip-flops using the K-maps drawn for excitations of the flip-flops in terms of the present states inputs. Step number 5, once the K-map has been obtained, we need to draw the logic diagram based on the minimal expression. So next, let us recapitulate the excitation tables of flip-flops. These we have already covered in the flip-flops lecture, but this will be very much helpful for us to design the synchronous counter. So this is the present state, next state table for SR, this is for JK, this is D for, and this is for T. So that means what if my present state is this, what input we need to put so that I can obtain this next state. Qn is the present state, Qn plus 1 is the next state. So when S is 0, R is don't care. If present state 0, next state will also be 0. So then if S is 1, R is 0. If present state is 0, next state will be 1. It will follow S. If present state is 0, next state is 1. Sorry, S is 0, R is 1, present state is 1, next state will be 0. It will follow S. If S don't care, R 0, it will be, next state will be 1. Similarly, in JK flip-flop, only change is over here. You can see, instead of 0, it will be don't care, and instead of 0, it will be don't care. And in case of the D flip-flop, we know in case of D flip-flop, what happens? If this is my present state, then next state it will follow the D input, right? And in case of the T flip-flop, what happens? Whenever T is 1, then next state will be toggle. Next state will get toggled. So you can see, whenever T is 0, next state will be 0, provided present state is 0. When T is 1, then what happens? If present state is 0, next state is 1, it will toggle, right? Again, when T is 1, present state 0, next state will toggle. When T is 0, there won't be any change in the next state. Now, let us proceed towards the design of the synchronous counter. Synchronous, we will first design a 3-bit synchronous up-down counter, okay, using the JK flip-flop. So first, what is the first step? First, we need to determine the number of flip-flops required. A 3-bit, first we will design the up-down counter separately. That means first we will design the 3-bit up counter, then we will design the 3-bit down counter, then we will merge it. So for 3-bit up counter, how many flip-flops do we need? We need 3 flip-flops, and the counting sequence will be upwards, right? 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1, again 0 0 0, right? Then so we need 3 flip-flops, okay, with 8 states. Then next what we have to do? Then next we have to draw the state diagram. So this state diagram is supposed to show all the possible 8 states: 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1. Once the state diagram has been drawn, then what we have to do? Then we need to select the type of the flip-flop, and we have to draw the excitation table for that particular flip-flop. Here we are using the JK flip-flop, so we will write the excitation table of the JK flip-flop. Okay, so first what you will write? This is the present state. We need 3 flip-flops. So this is let's say, so this is present state Q3, Q2, Q1, and this is my next state Q3, Q2 and Q1. All right. So let's say Q1 is my first flip-flop, Q2 is my second flip-flop, and starting from the left, Q1 is my first flip-flop, Q2 is my second flip-flop, and Q3 is my third flip-flop. Okay. So first I have to, this is my present state 0 0 0, then what will happen? If this is my present state 0 0 0, next state will be up counter, right? 0 0 1. Then present state 0 0 1, next state 0 1 0. Then again present state 0 1 0, next state 0 1 1. Then again present state 0 1 1, next state 1 0 0. Then again present state 1 0 0, next state is 1 0 1. Present state 1 0 1, next state 1 1 0. Next present state 1 1 0, next state 1 1 1. Present state 1 1 1, next state 0 0 0. Right? Now, first look at the LSB. Like say for Q1 flip-flop, this is my present state and this is my next state, right? What we have seen, now we have to write J3, K3, J2, K2 and J1, K1 corresponding to each Q1, Q2 and Q3 flip-flops, right? So for Q1 flip-flop, present state 0, next state 1. What we have seen in the excitation table from JK flip-flop, when 0, 1 means 1 don't care. So J1, K1 we will write 1 don't care, right? Then at the same time, you see Q2, present state 0, next state 0. 0, 0 means 0 don't care from the excitation table. Q3, 0, 0 means 0 don't care. Same process we have to follow for all the 8 states. Q1. Q1, what will happen? Present state 1, next state 0. 1, 0 means J1, K1 will be don't care 1, right? 0, 1. 0, 1 means 1 don't care for J2, K2. Then Q3, present state 0, next state is 0. 0, 0 means J3 will be 0 don't care. Okay, same process for this one. Q1 is 0. Then next state it is 1. So 0, 1 means 1 don't care. Then for Q2, 1, 1. 1, 1 means don't care 0. And for Q3, 0, 0 means 0 don't care. So likewise, we have to do it for all the possible 8 states, right? Now, if you observe one thing from here, you can see that J1 and K1, J1 and K1, they are either 1 or don't care. Okay, so it will be 1. Okay, that means the K maps for excitations based on the, we need to draw now the K maps based on these excitation tables. Okay, so we don't need to draw any K map for J1, K1 because it will be 1, because all the combinations are either 1 or don't care. So we need to design the K map for J3, K3 and J2, K2. So for J3, you see for which, for J3 where you are getting 1 and don't care. So you take that input combinations. So this is a 3 variable function. We need to have 8 cells. So here you write, only focus on this present state. Okay, you write Q3 and Q2, Q1. Q3, Q2, Q1 in the present state are your variables. So this is my Q3, this is my Q2, Q1, right? Now for J3, you can see starting from 3 to 7. So 3 is 1 and then 4 to 7 all are don't care. So you just put the don't care, then you group. So this one will be J3 is Q2, Q1. Similarly for K3, you see the don't, where you are getting for which input variables in the present state you are getting the don't care and the 1 combinations. So put it right here, and the K map for K3 it is coming as Q2, Q1. Next you look for J2, 1 and don't care you are getting for which input variables. So accordingly you have to group over here. J2 is coming 1, and for K2 it is don't care for 0, 1, 4 and this is 5. Okay, and this is 0, 1, 4 and 5. K2 is don't care for 0, 1, 4 and 5. Okay, and it is 1 only for 3 and 7. It is 1 only for 3 and 7 and other don't care. So Carnot map for K2 is 1. Okay, so my up counter, I got the expressions for up counter. Okay, now same process I need to follow for down counter. Okay, so next when I am drawing the down counter, first what we have to, now we know that I am designing a 3-bit down counter. So I need a 3 flip-flops I need, and it will have 8 possible states, right? And I am using JK flip-flop. So down counter, how it will count? 0, 0, 0, 1, 1, 1, 1, 1, 0, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 0, 0, then 1, 1, 1, right? So this is my down counter. Okay, so it is first 0, 0, 0, then 1, 1, 1. 0, 0, 0, 1, 1, 1, then 1, 1, 1, 2, 1, 1, 0, 1, 1, 0, so 1, 0, 1, like that. 0, 1, 0, 2, 0, 0, 1, 0, 0, 1, 2, 0, 0, 0. Likewise, it will count, right? So here also you follow the same process. When my Q1, look, you put here J3, K3. These are my required excitation inputs, right? If this is my present state, in order to generate this next state, what are the excitation inputs we have to follow? That is why this excitation table should be always in your mind. So J3, K3, J2, K2, J1, K1, all these inputs we are giving to our flip-flops. Now for Q1 flip-flop, what is the present state? 0 and 1. Next state is 1. So 0, 1, when present state is 0, next state is 1, what will be my J and K inputs? 1, don't care. Q2 present state 0, next state 1, what will be my J and K inputs? 1, don't care. Q3 0, present state 0, next state 1, what will be my J3, K3? 1, don't care, right? Similarly, likewise, we have to do for all the 8 combinations, and next you will, here also you can see J1, K1 will be 1 because it is either 1 or don't care. So we don't need to draw the Carnot map for J1 and K1, but rest of these J2, K2, J3, K3 we need to get the Carnot map. And see, for each column J3, you see you are getting 1 and don't care for which present state input variable. So you have to get the Carnot map for all these J3, K3, J2 and Q2. Okay, so if you observe over here, for up counter you are getting J2 equals to Q1, K2 equals to Q1. But for down counter you are getting J2 equals to Q1 bar, K2 equals to Q1 bar. For up counter you are getting J3 equals to Q2 Q1, K3 equals to Q2 Q1. But here down counter you are getting J3 equals to Q2 bar Q1 bar, K3 equals to Q2 bar Q1 bar. So from these design equations of the up counter and the down counter, we can see that both the cases J1 and K1 1. Okay, so for up down counter 2, J1 1 and K1 1. And for the up counter J2 K2 is Q1 and down counter J2 K2 is Q1 bar, that we have just seen. So for the up down counter J2 K2 will be Q1 into up plus Q1 bar into down, right? Similarly for the up counter, because one is just the complementary to the another. Okay, so for the up counter J3 K3 we have seen Q2 Q1, and for the down counter what we have got for J3 K3 Q2 Q1 bar. So for an up counter can we write like this: J3 equals to K3 equals to Q1 Q2 into up plus Q1 bar Q2 bar into down. So we need to use a control signal named as M. So if you put M equals to 1, it will count upwards, and if you put M equals to 0, it will count downwards. So if you combine all the above equations and then what you will get, J1 K1 is 1, J2 K2 is this one, Q1 into up plus Q1 bar into down. That means this control signal we have considered as M. So it is Q1 M plus Q1 bar M bar, and J3 K3 is what we have got. Just receipt Q1 Q2 into up plus Q1 bar Q2 bar into down. That means Q1 Q2 up means M plus Q1 bar Q2 bar into down means M bar. So this is your final logic diagram. So we will have 3 flip-flops. This is my first, Q1 is my first flip-flop, Q2 is my second flip-flop, and Q3 is my third flip-flop. So all the flip-flops, it is a negative age triggered flip-flop. All the flip-flops are clocked simultaneously, right? And that is what we know for the synchronous counter, right? And for J1 K1 it is 1. Okay, so this is the control signal. What is my flip-flop 2 J2 K2? What will be my J2 K2? It is Q1 M plus Q1 bar M bar. So this is M, Q1 M. We are giving it to an AND gate, and Q1 bar M bar, and it is going to an OR gate, and that input we are giving to J2 and K2 to the second flip-flop, right? And for J3 and K3, what we are giving? Q1 Q2 M plus Q1 bar Q2 bar M bar. So for J3 and K3, this is Q2, and this is my Q1 Q2 M, and this is from here we are getting Q2 bar Q1 bar M bar, right? Q2 bar Q1 bar M bar. So that is going to an OR gate, and it is finally going as an input to both the J3 and K3, right? This is how we are designing the synchronous counter. We just have designed the synchronous counter, 3-bit synchronous counter. Okay. Next, what we will design the synchronous BCD counter. That means mod 10 counter using the JK flip-flop. So here, what is the first step? BCD counter, it is nothing but a mod 10 counter, right? And it is a decade counter. It has total 10 states. All right. Now, it requires how many flip-flops? It requires total 4 flip-flops, because capital N less than equals to 2 to the power n. So, if this condition is getting justified, 10 less than equals to 2 to the power 4, right? So, 4 flip-flops, we know it can have maximum of 16 states, and after the 10th clock pulse, the counter will reset. So, states 1010 through 1111 are invalid. Okay, that means the entries for the excitations corresponding to invalid states are don't care. Next, we need to draw the state diagram. Next, we need to identify the type of flip-flop and the excitation table of that flip-flop we need to write. Then from the excitation table, we need to draw the Carnot maps, and from the Carnot maps, then we need to finally draw the logic diagram. So this is the state diagram of your BCD counter, synchronous BCD counter, right? So what can we see over here? This is a how it will count 0 0 0 to 0 0 0 0 0 0 1 1 0 0 1 0. Likewise, it will count till 1 0 0 1, because after that rest of the states are 10 to 15, rest of the states are invalid. Again, after 1 0 0 1, it will go to the 0 0 0 state. Okay. Next, what we have to do? Next, we need to draw the identify the flip-flop. We are using here JK flip-flop, so we need to draw the or write the excitation table for that JK flip-flop. So here we have 4 inputs, right? Q4, Q3, Q2, Q1, and next state also we have Q4, Q3, and Q2 and Q1, right? So here same process we need to analyze. So if Q1 is my present state, Q1, here it is next state. For present state Q1 0, next state Q1 1. So what will be my J1 K1? 1 don't care from the excitation table. Q2 0 0 means 0 don't care for J2 K2. Q3 0 0 means 0 don't care for J3 K3, and Q4 0 0 means 0 don't care for J4 K4. Likewise, we have to write it for from 0 to 9 for all the possible input combinations, and we need to get this excitation table. Now for each, here also you can see for J1 K1, it is either 1 or don't care. So J1 K1 both will be 1. We don't need to draw the Carnot map for J1 K1, but all these J2 K2, J3 K3 and J4 K4, we need to draw the Carnot map. So for each column we need to see the input variable combinations for the present state for which we are getting 1 and don't care. So we need to, since here are 4 variables, so 16 cells will be there, right? So we need to get the Carnot maps with 1 and don't care for all the, but we need to loop the present state Q4, Q3, Q2, Q1 combinations only. So we have to get the Carnot maps for all J4, K4, J3 and J4, K4, J3, K3, J2 and K2 here, right? So once it is obtained, since we know J1, K1, it is 1, all 4 flip-flops you just draw JK flip-flop, then all these 4 flip-flops, these are negative age triggered flip-flop. All the flip-flops are clocked simultaneously. So for the first flip-flop J1, K1, it is getting 1. So what is the J2, K2? J2 K2 you are getting J2 is Q1 and Q4 bar. Q4 bar and Q1 we need to give to an AND gate. So this is directly going to J2. And what is my K2? K2 is Q1, so we can directly give it. And what is my J3? J3 is Q2 Q1. So how we will give? This is my Q2 and Q1. You can give from here this line. This is AND gate. And K3 is Q2 Q1. So K3 is Q2 Q1. You give, this is J3 is Q2 Q1, no? So just tie it together. Next, what is J4? J4 is Q4 bar Q1. This is Q4 bar. This is Q4 bar. J4 is Q4 bar and Q1. Okay. So this is AND gate. It will go to the J4. Sorry. J4, what is the expression of J4? J4 is Q3, Q2, Q1, right? So J4 is Q3 and this is my Q2, Q1. So that is my J4. And what is my K4? K4 is Q1, right? So K4 is Q1. You can directly give from here. Okay. So my logic diagram is also completed.